Hey there, sixth grade. Today we're talking about equivalent fractions and basic proportions. So we've talked about equivalent fractions probably in your prior classes, and we've talked about them this year, but we want to talk about them again and also use them in some specific word problems that hopefully will make your life a little easier and help you solve some word problems like a champ. So get your title and date, and let's check it out. The notes you need to take today are that equivalent fractions express the same amount using different numbers. So they're always about the exact same amount, and we've showed that in a number of ways, but I'll show you just again that we're expressing the same amount. So what I mean by that is, well, we know that fractions express a part of a whole. So let's say we have, this is going really slow. If we have 1/4, that's a fraction. 1 is shaded out of 4 total pieces. Now I'm going to draw some more cuts. I'm going to double the number of pieces, but I didn't shade anything more. So you should agree that hopefully that I did not change the amount of that whole shape that was shaded. That's the same portion of the total. That's the same part of a whole that's shaded, but now it's 2 out of 8 pieces. And the reason that makes sense is because I doubled the number of shaded pieces because I doubled all the pieces. So of course the one that was shaded got doubled, or the ones shaded will get doubled. So that's why we know that equivalent fractions are created by multiplying or dividing both numerator and denominator by the same number. So that's what happens when we create equivalent fractions. The other note I ask you to take down is that ratios compare values with different units. So they look a lot like fractions when we write them out. So for example, I might write for you that you could travel maybe on a bicycle. You could do 40 miles. Oh, that looks so bad. 40 miles in 3 hours. Now you might be saying to yourself, oh, that kind of looks like a fraction, but it looks like an improper fraction. But the thing about ratios is they have different units. So we have not part of a whole hour, or part of a whole fraction bar, or pi, or whatever it is. And instead we have miles on top, hours on bottom. Those units don't go together. But we're going to see that it's useful to write things like this as if it were a fraction. But you don't need to worry about improper fractions. You just do need to write the appropriate units with the appropriate numbers. So that's what I say down here. Make sure you match up units. So if we're going to try and figure out how many miles could you do in 1 hour, I would divide top and bottom by 3. If I was trying to find out about 6 hours, we would multiply top and bottom by 2. But it's important that we keep the same unit on top and on bottom. There we go. Okay, so you make sure you match up units, and then we're going to treat them just like equivalent fractions, but they're actually equivalent ratios because they have those different units. So let's go ahead and see what this looks like in practice. Check out example number 1 with me. It says, write equivalent fractions with bigger and smaller digits than 8/18. Okay, so I got to have 2 equivalent fractions if one's going to have smaller digits and the one's going to have bigger. Now, let's do bigger digits first. I know a lot of people like to multiply. So let's do 8/18, and we need to create something that has the same value but larger digits. So a lot of people like to multiply by 2, but let's actually multiply by 4. Let's kick it up a notch. So 8 times 4 is going to give us our new numerator, and hopefully you have that fact memorized. That'd be 32. But if we multiply the numerator by 8, we've got to multiply the denominator by 8. We can do this mentally. 4 times 8 is 32. We just did that. But we got to carry the 3, and then 4 times 1 is 4, plus 3 is 72. Okay, we got 72. Now for 8/18, if we want smaller digits with an equivalent fraction, we'll have to divide numerator and denominator, and that's fine because we see that these are both even. So both divisible by 2, and that's actually the only common factor that they have. So we'll divide top and bottom by 2. And what we're going to get is we're going to get 4/9. And that makes sense. That's a simplified fraction. It can't be simplified anymore. They have no shared factors, so that's the simplest form. So we now have a bigger form of the same value and a smaller digit form of the same value. So we can write the same value with different sorts of digits. Let's move on. This next one, I'm going to show you equivalent ratios and how to put them to work. And this is a more serious problem. And this is true, sadly. It says use the equivalent ratios to solve. Some studies show that women in the United States make about 81 cents for every dollar that a man makes at the same job. And studies also show that women are not necessarily worse and men are not necessarily better at doing specific jobs. So this is employers who are unfairly giving men more money or actually giving women less money for the same amount of work. So this is something we need to address. And it says, if this wage discrimination exists and a man makes $13 an hour doing a job, how much would a woman make? So the first thing we need to do is just write the ratio that we have already. So the ratio for, so if we have 81 cents for a woman at a job would earn $1 for a man doing the same job. We want to know if the man is making $13, how much will the woman be making? That looks like 13 million, but it's just for men. And the reason we're going to look at this problem is because, 81 cents a dollar, rounded up, it's pretty close. But let's see what it actually turns out when you're talking about the real value of a job. So what did we do to the denominator in this case? Well, we multiplied by 13. So we're going to be able to solve this and figure it out if we just multiply the numerator by 13 as well. So let's do 81 times 13. And I'm going to choose to do 13 times 81. That's the, oh, that looks awful. That is the commutative property of multiplication. 3 times 5 is the same as 5 times 3, whichever way we want to multiply them. So 1 times 13 is 13. That's part of the reason I did it. We need a placeholder because now we're multiplying by the tens place. 8 times 3 is 24. Carry a 2. 8 times 1 is 8, plus 2 is 10. So a woman would make 1,503 cents. Okay. To actually get an idea about this, 1,053 cents. So to make this actually mean something to us, why don't we convert that to dollars? And we can do that just by saying, well, how many cents are in a dollar? 100. So we need to divide this into groups of 100. So whenever we divide by 10, we move the decimal over once. Whenever we divide by 10, we move the decimal over twice. So this is $10.53. And that doesn't seem fair, does it? The man will get $13 and a woman would just get $10.50. So this is why this is a topic of conversation and something that we really need to address. And that's also why equivalent ratios will help us, or proportions will help us to solve certain problems. We'll talk more about that one in class tomorrow, see what you guys think about it, and think about what we should do. But for now, I'm going to leave you with 2 problems on your own. The first one says, write equivalent fractions with bigger and smaller numbers than 10/15. So that's kind of like the first example we did. Second one is another word problem for equivalent ratios. It says, Takeru Kobayashi can eat 50 hot dogs in 12 minutes. If he can keep up that pace, how many hot dogs can he eat in 48 minutes? And that's actually true. He can't eat 50 hot dogs in 12 minutes. He probably wouldn't keep up the same pace, so it probably wouldn't be a proportion. But let's say he did this over 48 minutes and he was going at the same rate. Find out what proportion or what value of hot dogs would make that be in proportion. And there's a picture of Takeru. All right, best of luck. I'll see you tomorrow.